Well, welcome everybody. Like I said, this mic's really loud, so I'm going to try to roll it a few inches away from my face. My name is Chris Love, and this is Anton.
Nice to meet you.
And I'm the founder of 𝐤𝐴𝐚𝐭 and yeah,
We are cloud and data engineering company. The office is here in the
want to hit this bit part? So we were talking earlier, we've got a good standard of people who are at least familiar with Docker containers. We'll use the word containers because really you don't have to use Docker to run Kubernetes. You have to use what's called a container engine, which containerd and other engines will actually execute containers that you're running. And it really starts with a container, right? And if you're not familiar with containers, the way I describe it, especially to salespeople, is it's a box, right? You need to deploy a piece of software, so you've got a binary, and you want to deploy it in multiple different places. It's easiest if you just put it in a box, and then a Kubernetes cluster can pull it down from an HTTP server. And there's a big difference between virtual machines and running virtual machines and running containers. Running virtual machines requires a lot of work. Anybody been in dependency hell with Ruby or Python on a virtual machine? Please raise your hand. Yes, all right. So if you're not familiar with what I'm talking about, you can run into issues where you're trying to run Python 2 and you pick up Python 3 libraries. Or you install a Python program and realize that you only have Python 3 installed in the machine and not Python 2. Ruby's even more fun, and I'll go back to the day Perl. Perl's even more fun because you start having path issues and you pick up these random libraries you're not expecting. Nice thing about containers is you're creating, it's both deterministic and hermetic. So hermetic's like jar, right? We take the piece of software and we seal it in that jar. We know exactly what's inside of our jar. And hopefully we don't have other stuff that we don't know about. Really the difference between having a virtual machine is you have your virtual machine, you have all your binaries, your libraries, and you have app-C, app-B, and app-A on it. And they're going to intermingle possibly. With containers, you don't. You have a box that runs inside of the Linux, it's called Linux namespaces, and it gets an isolated network, it gets an isolated file system, everything's sealed inside a nice little package for you. So here's an example of a Docker file. This is actually a little bit more complex Docker file. This is building Go. So you'll notice the from statement. The from is what's called a base container. So that's the first container that you're pulling down. We're running a couple of Ubuntu commands, which is an apt-get update and an apt-get upgrade. All that does is it ensures that your container and the operating system that's inside your container is updated. We then set a working directory that we have. Then we copy in the source code. So in the same folder as this, what's called a Docker file, is a bunch of source code. And we're simply copying it in there, and then we do a run command, which runs go build. What happens now is we have binary, right? And this is actually a newer feature in Docker where you're able to have multiple containers defined inside the same Docker file. So again, now we have the same steps again. But you're noticing, why are we running apt-get update and apt-get upgrade again? It's because, remember, we have our sealed jar. The first container that we ran is its own sealed jar. We built it, and then we take the next thing, which is another sealed jar, create the work directory, we're copying now binary, a couple files in, we run a couple more Linux commands, and we're exposing the port, and then we have an entry point. One thing that we're not doing, which I don't like inside this container, is we're running this root, but that's beside the point. So in essence, it's a very small subset of actions, such as from, run, worker, copy, entry point, etc. that you can execute within a container. And what happens is you build this container, let's say CI/CD, or you build it locally in your laptop for a Mac, and then you push that container up to the registry, which is again is an HTTP server, and you can then a Docker engine component can then access and pull down that container. This also operates in Windows. Neither Anton or I are Windows experts, so if we're going to play on our Mac and not play on Windows, Kubernetes does run on Windows as well. It is limited. The support on Windows is a little bit less. Okay, so let's talk about architecture. Lots of diagram, lots of moving parts here. So within a Kubernetes cluster, you need to know some buzzwords. The first buzzword is what's called a node. A node is a unit of compute. And it is every unit of compute, in other words, every server within Kubernetes is called a node, even if they're on the masters. And we also refer to the master as the control plane. So within Kubernetes, we have an API server that you use a binary called 𝐾 to talk to, or you can directly call the API server. From there, we have scheduler, we have control manager, our database is etcd, it's a key value pair database. And then you have those sort of pods on the control plane, and typically if you're using a managed service like GKE or EKS, so EKS is Amazon's managed service for Kubernetes, GKE is Google's managed service. You actually don't see the control plane, you don't see your masters at all you see are your nodes. So within the nodes, we have various components. One of them is called a pod. We'll get into what's called primitives or API objects for Kubernetes in a bit. Within there, you have different binaries running, kubelet, 𝐶Advisor, 𝑃𝑒RSI. You also have networking. So that's a real quick crash course in architecture of Kubernetes. There's a lot more going on here. The interesting thing is kubelet. Kubelet controls your pod lifecycle. And we'll talk about pods a bit more, but I'll give you a preview here. A pod is one of the smallest API objects that's defined within the Kubernetes API. It wraps one or more containers. So if you need to deploy a container, you're usually deploying a pod or further up abstraction of what a pod is. So kubelet is a nice binary that does a bazillion different things, including creating, destroying, updating, restarting pods. That's primarily what it does, is pod lifecycle. Does some stuff in the lifecycle as well. Any questions? Or we'll take more questions at the end. So, as I mentioned, we're talking about basic Kubernetes objects. We've got a pod, a service, a PB or PDC, and a namespace. We're going to go into all these a little bit later on. But like I said, the smallest basic object within the API is called a pod. And it's actually a Golang struct, believe it or not. So it's actually an object defined that's inside the object, and that's how we control the Kubernetes server. We also have services. Services are how you're able to communicate to pods, either inside the cluster or outside the cluster. You've got PD and PVC, which are persistent volume planes and persistent volumes. The developer will use a PVC, and possibly an admin will define PVs, which are actual volumes. They can be set volumes, they can be ES volumes on Amazon. Basically, it's a piece of disk. We have namespaces, which are segmented everything together. And then we have our high-level abstractions. And let's go to the next slides. I think I'm ahead of myself, but we're gonna know. Yay.
So I'm controlling this. I'm just going to run some simple kube control commands to emphasize the using managing Kubernetes cluster from a user experience perspective. So I'm running Kubernetes cluster on my laptop. It is now shipped with a new Docker for desktop edition, so you don't need to work hard to have full-blown Kubernetes cluster running on your laptop. And we see that I have one node here called Docker Desktop. We will try to describe this node. And see the information that Kubernetes dumps us to show different parameters that are used to manage your nodes. One of the most important parameters or facilities that Kubernetes use to manage lifecycle of all objects in Kubernetes system is labels. Kubernetes uses labels for everything to connect basic parts to their abstractions and to attribute deterministic method of configure the way your pods talk to service, or the service relates to ingress controller, or the way you want to schedule your pods, etc., etc. So we use extensive labels. Labels go even up to your CI/CD system. We use labels for everything. We have annotations, labels. We also have system information, amount of memory pressure, disk pressure, processes. We have node capacity, the amount of RAM I have available in CPU, of course. And it also prints my Docker version, my OS version, and containers or pods that are running on the specific node. Right, so it is that easy to show the information of your node in very good way.
And one quick thing that I'll mention is that you're only seeing a single node on this cluster. So you're seeing the master that's up. If you do a production cluster, you'll see 3 masters that are up and 100 nodes that are running. Right. So you won't just see a single node, you'll see all the nodes.
Now, the very good thing I want to emphasize for running this command, kubectl gets posted in the namespace called kubesystem, is the fact that Kubernetes internal components are also running as Kubernetes primitive pods. So Chris mentioned earlier today, etcd and API server, we see them here running as pods, right? So Kubernetes manages its own internal components through the standard primitives. So namespaces. Namespaces are used to create virtual clusters within your Kubernetes cluster. They actually divide the cluster into namespaces from a host name perspective or service name perspective, network segregation, role segregation, security purposes, etc., etc. You can imagine a scenario where you have a cluster serving your R&D team, and each and every developer may have his or her own namespace and work within this single pods. So as Chris mentioned earlier, pods are the tiny units that Kubernetes uses to run containers. Pods facilitate shared network, shared IPC, shared Linux namespace, shared volume for multiple containers that make a pod, and all of the containers that make a pod necessarily run on the same node. Deployment is a high-level API or controller that is used to declaratively manage pod lifecycle. So we use deployment to update pods, update new versions, pods, etc., etc.
So, just stay on the slide for a second. One thing I'm going to add is, if you're doing Kubernetes for the first time, you're primarily going to run deployments. You know, everybody's heard that, yes, we're going to do more microservice, right? And stateless microservice within Kubernetes. This is the predominant object that's used for microservices for beginners. This is what you'll touch. Pod's cute, you know, but deployment is real. You're able to do rolling updates. You're able to set percentage of pods that are going to be able to do a rolling update. You're able to set how many replicas of pods you have. So basically, you see deployment, we've got a Node.js, Node.js, Node.js. Each of those are pods. In a replica, you can have 40 of those. Stateless microservices running across your cluster.
So the demo, I wanted to emphasize the easiness and how Kubernetes can actually save time deploying anything from stateless application to stateful your code or some third party. So I would like to show you, if you're familiar with Terraform, anybody? So Terraform is a software-defined infrastructure. It's a DSL used to create cloud resources like EC2 machines in Amazon, etc., or configure your cloud infrastructure. So I'd like to show you amount of code lines necessary to deploy 𝐚𝐥𝐰𝐴's server in Amazon, Terraform. All this code, and it's hundreds of lines.
It's a lot.
It's required to run just one 𝐚𝐥𝐰 server. Let's go back to Ventus, and this is our deployment manifest. That's it. And it has the same functionality as the code that I previously showed. So it is quite easy for a developer to spawn his or her own environment and operate.
If you leave that there for a second, �YAML. Who knows �YAML? It's a JSON language. If you do Kubernetes, you will learn to hate �YAML. But it's YAML, and you'll learn to validate your YAML and make sure you don't have tabs in YAML. I've never done that before. But basically you notice the API version, so it's a versioning tag of different versions of, say, deployment objects. You have your kind, you have metadata. For instance, we're going to put it in the default namespace. We have selectors. You notice match labels. We don't have all of our labels in here, but that's all right. And then we have a spec with containers. This is actually a pod. So if you look at the spec, we're going to run containers, and we're going to run the 𝐚𝐥𝐼𝐴 image with the latest package. You ever do production, what we're doing.
This is a definition of service that we previously discussed. Service is used to route traffic from clients to a port, or to a number of nodes. So the way we connect our deployment of our loads to the service is labels. So we give this label here, and previously we had the same label in our deployment manifest. Right? Very good.
Perfect transition to talk about services. Yes. Yes. Test. There we go. So we've got 4 basic different types of services within a Kubernetes cluster. The first is cluster IP service. We've got node ports, load balancers, and external names. According to Anton, this is a little bit of a joke. External names are used a lot. I've never used external names before, and we forgot to include this slide about external names. So you want to go on to the next slide for me. So here's the use case. You use a cluster IP service for. A microservice within your cluster needs to talk to another microservice within your cluster. It does what's called a cluster IP service. It gives it a DNS name, and microservice A is able to look up via DNS microservice B. It's only within the cluster. The nice thing about it is you can have multiple pods. As you see here, we have multiple pods behind the service that acts as a load balancer. If the pod is not in a ready state, traffic won't flow to it. If the pod is moving from one node to another, traffic won't flow to it. Next one is the load balancer. So Kubernetes automatically, or when Kubernetes runs in the cloud or in some bare metal situations, it will actually control the infrastructure within the cloud. So when you deploy a load balancer service, say in AWS, it will create an elastic load balancer for you that's outside of the cluster automatically. It will then route traffic from your services directly to that load balancer. So you're able to get an external IP address. So say you have a WordPress site or your Node.js site, which is your external site, and you want to expose that to the internet. One option that you have is a load balancer. And if you remember the Kubernetes controller manager way back when, on a few slides back, it actually has a cloud plugin. So it can do Azure, it can do AWS, it can do GCP, it can do DigitalOcean, it can do bare metal in some situations. VMware just released a huge release about Kubernetes, where they're going to have Kubernetes built into their ESXi server, so they'll be making NSX calls outbound to create those load balancers in NSX and bare metal. Node ports to be specific use case for as a service. What it does is it creates a node, or sorry, it doesn't create a node. It creates a port on every node in your cluster. And with this one, we created it on port 30,000. So every one of those nodes is going to have a port 30,000 that's joined with a specific group of pods. And for instance, one of the use cases that we had to use node port, there's a couple that I can name off the top of my head. One is the big ingress controller, which we're going to talk about in a few minutes here. The other is running big data solutions such as Cassandra. We had a use case where we ran Cassandra on ginormous nodes. They were R410XLs. Had about 96 gig. And we had one Cassandra node one instance of Cassandra per Kubernetes node. I also mentioned ingress controller. So ingress, there's a little bit of complexity around the name ingress. So let me give you some background here. Ingress is an API type within the Kubernetes server. So again, there's pods, there's services, jobs, deployments that we covered, right? Now we also have what's called an ingress. Ingress is very interesting because it's implemented in various methods. So there's an ingress controller that's called an 𝐚𝐥𝐰𝐴 ingress controller. So that has to be installed within the cluster besides using ingresses. So you have to have some sort of operator or controller that creates the ingress for you. Within GKE, it's kind of unique because or actually GCP in general, so in cloud in general, it has an integrated ingress type or integrated ingress controller, which spins up specialty HTTPS load balancer. So why do we care about ingresses when we have load balancer services? There's actually customers that hit limitations on the number of load balancers that you can have in a VPC. I've seen that we're running about 300 different internal load balancers. That's an issue. So what an ingress allows you to do is take the URI of an HTTP service. So say you have mysite.com/food. That's going to go to one set of pods, one deployment. You have mysite.com/bar. That's going to go to another set of pods. This is pretty cool. It'll also do DNS names. So if you have mysite.com or if you have yoursite.com, you can get redirected to different Nginx or Apache servers, just like the virtual hostings within Apache. So we've got a bunch of different other controllers. Yes. So load balancers will pop up, say an elastic load balancer in AWS, right? And there'll be one IP address that goes to one set of pods. An ingress will also create a load balancer or use ingress or Nginx ingress controller, and it can run multiple different URIs, okay, and multiple different DNS names. And UDP works better with EWPs or elastic load balancers and regular load balancer services. TCP and of course HTTP and HTTPS or TCP works better with load balancers. HTTP works better, and HTTPS works better with ingress controllers. Great question. So we've got some more primitives here, more API objects that are called controllers. Same as deployment. Deployment's a controller. We've got jobs. Basically, run these pods until it's success, and we'll restart them when they run. We've got also a cron job. Everybody's probably familiar with the term cron job. Run this job at a specific time. We've got a daemon set, which is pretty handy with stuff like logging utilities. So what a daemon set will do is it'll create the same set of pods on every node that you deem it to be. So typically you want to have logging on every single node, right? You want to have logging, you want to have networking, you want to have your basic administrative utilities, and a daemon set will put those pods on every one of your nodes. Stateful set, as per the name, I talked about it in the presentation this morning, it was created specifically for running stateful applications. We talked about persistent volume claims and persistent volume claim controllers. We've got to have, we have a web application or we have a stateful application, we need to store the data somewhere. There's also, one of the ones that we didn't mention here is there's a drive type that's called an empty dir. And what an empty dir does is it creates actually a volume local on the local disk of your node. So you can have a partition and not have a external volume. But if you need persistence, you'll use something like an EBS volume, or you'll use an Azure disk, or GCP disk, or vSphere volume, SAPs, etc. Supports a lot of different volume types. We're missing the VMware volume, vSphere volumes there, even like some of the big hardware companies have specific types of volume controllers they can use within Kubernetes.
And so I would like to add here that a lot of the traditional storage vendors now are developing CSI drivers to support Kubernetes on their storage subsystems, like NetDrive.
Yeah, EMC, that was the one I was thinking of. And we talked about stateful sets. So you need to have, and this is something that's a little bit more advanced. You'll either understand what you're getting into with stateful applications or Kubernetes, or you're going to learn really, really fast what you got into. With stateful sets, it provides unique identifiers. So if you create a Cassandra instance or Elasticsearch instance, it's going to take the name of the stateful set and put a -0 on it for you. And then you're going to use a specific type of service. It's called a headless service. It's going to give you name resolution inside your cluster so that you have, Elasticsearch, that's 0, and your clients are able to find that Elasticsearch client. Also gives you stable persistent service, or storage rather. So the big deal is that you have a persistent volume 0 and you have Elasticsearch instance 0. You want that persistent volume 0 to fall around Elasticsearch 0 wherever it's at. So if you upgrade Kubernetes, typically you destroy nodes. You actually drain the node, coordinate, destroy it, and all your pods are moved over to the new node. Well, your EBS volume has to do the same thing. It has to follow the pod over to the new node. And it's really important that the pod that starts up, who thinks it's Elasticsearch 0, has a host name Elasticsearch 0, and has this information that says it's Elasticsearch 0. Also, ordered and graceful deployments and scaling. So if you need to add 20 more Elasticsearch clients, you hit a button, it scales out, and you get, 20 more, but it goes, 15, 16, 17, etc. Also, the same thing happens in rolling updates. When you have to upgrade Elasticsearch, it'll do it in sequential order. Elasticsearch is a bad example because sometimes you have to shut it down and restart it. Cassandra's a little bit better example, where you're able to roll out a rolling update, start at 0, 1, 2, 3, 4, etc.
So when we manage a real production environment, Kubernetes, you end up managing, hopefully in your source code, hundreds of deployment manifests, like what we've shown previously. To ease that process, community has come up with a project called 𝐴𝑚, and 𝐴𝑚 is similar in the concept to package management systems you are familiar with if you're working with Linux, like RPM or different packages. What it does is it provides you with a templating engine to create deployment manifests by compiling your template with the values that you apply during the deployment time. So charge ISIC to version, store, share between teams, and you can provide the information during deployment that is specific to your environment while keeping the charge. suitable for multiple deployments. Like, for example, you have engineer server, dev, deployment, staging, and the only thing that changes within the environment is probably your database URL. So you're able to reuse the same Helm chart across all your systems, but you can actually pass a variable on the installation or use a variable file to specifically specify the relevant database URL. And here, that's how the Helm chart looks like. It has a metadata file with information about the Helm chart, version, etc., maintainer, it has templates directory with all your deployment manifest templates, and it has a value file that is used to compile the deployment manifest to, for example, you're running out of Java application using the Helm chart, and you want to update your Java heap size, so you don't have to update your deployment manifest, you just have to specify new heap size value in your values file, and that's it. Done, it is easier to maintain this code in your Git because you want to see the difference between this release and that release. All you do is git deep on the red file and you see the change.
And there's much different options besides Helm. CI/CD is one of the big things that's being worked on, and making deployment simpler and development simpler on Kubernetes is one of the big focuses that the community has. So Helm's not your only option, it's a very, very wide use option.
So I'm going to run just some commands to show you how we can use. So we have something called 𝐸_search. And what it actually does, similar to RPM, QA, or something, that if you're connected to RPM or Debian repository, it shows you all the RPMs available. Same here. This is an internet repository for stable Helm charts developed by community. So you have them all available for you for immediate installation, and I will show you how easy it is. So you can actually get out and install Compound right out 15 minutes. We're done. So what it creates here, it creates a deployment called 𝐸𝐸_search, and it creates a goal. It creates a service type clustering. Right, so we can this, and we have a deployment that release with chart, name and version content, with application version, namespace specified, and you can actually manage the lifecycle of your application through Helm. Let's show you how the chart looks like. So that's the Helm chart that is deployed. So it has a value file that specifies, for example, replica count, the number of ports running on this specific deployment, image that is running, image for policy, open with metadata information, load balancer settings, ingress controller settings, and very important parameter that you are advised to use in your Kubernetes installation is resources. So you can specify the amount of memory and CPU necessary for your application to run successfully. You can also specify limits. For example, you have a Java server and you suspect that your Java server memory consumption will grow because of some memory leak. So you can specify that to run my Java server successfully, I need at least 2 GB of RAM, but not more than 8 GB of RAM. So Kubernetes will actually, if you specify this here, Kubernetes will actually kill your application once it's requested 8 GB of RAM and restart it. Right, so that's the data file, that's a template. It includes exactly as the deployment manifest we have shown previously, but it contains template history information.
Yeah, it's using built-in templating language. So it's a little bit less, a little more than typical built-in language, but it's really documenting how to use it.
Yeah, from my experience, large organizations use HAM extensively because you can have a group that develops corporate Elasticsearch and you want to ship it to other teams. So shipping deployment manifest is cumbersome. You have to version them somewhere, you have to pop them, and you have to provide versions and atomic package. So HAM is a means to do that. Moreover, you can facilitate flow control in HAM. For example, you can have if environment is bad and 𝐷𝐸 equals 2, if environment is strong, then 𝐷𝐸 equals 8. And you don't have to recall that, you have set this once, and it runs all through the life cycle of your Android.
Yeah, sure.
Yeah.
So these values go into the templating language and are rendered out by 𝐷, and it creates the deployment YAML for you. Yeah.
This one? Yeah, replace various template. Then you have the hierarchy, like many templates, usually go templates, standard. Yeah.
We can talk a little bit more about help. Yeah, if we're running up here against the time. So let's talk about auto-scaling. Actually, you're going to scale deployment, and we skipped over that, but that's all right. So one of the biggest aha moments I had with Kubernetes is I had Puppet, I had Chef. I'm like, why do I need containers in Kubernetes? It's yet another thing that I have to learn, and I love my Puppet server. So what I had was I was working on a demo application. I forgot to tune Java, and I did some load with the demo, and I was running 10 replicas of the same Java web application. And what happened was the memory, I didn't set the heap size. So the memory, went over the size of the container that was set up, and Java crashed, right? Java never reset. So what I did was like, I gotta go to my container, and I gotta set heap size of my container, and I gotta do my deployment, and all right, hold on a second, I got 5 minutes before my demo. Wait a second, I'm in Kubernetes. There's a simple command to scale replicas within Kubernetes and do deployment. Hit a button and went from 10 pods to 300. There's a lot of power on that. In busy holiday season that's coming up, when our websites get hit by people wanting to buy stuff, it's wonderful when you can just hit a button and you suddenly have so much more capability for load. Another thing is clusters actually will auto-scale as well. So not only can you scale replicas, but you can auto-scale the number of hosts you have in the cloud automatically. So if a host hits a certain CPU percentage, it's going to create another node for you. When the node gets trained properly, it's going to remove the node for you. Also, we have 2 different types of automatic auto-scaling as well. We have what's called horizontal pod auto-scaling. Remember how I scaled from 10 to 300 servers on 10 to 300 pods almost automatically with a keystroke? With horizontal pod autoscaler, it'll do it automatically for you. So say you set up your deployment, has 30 pods in it, gets a bunch of load, CPU starts going up. It'll put out another 10 pods for you to balance out the CPU. Now you can get all kinds of fun stuff with this as well, where you don't quite have enough CPU set up on your Elasticsearch server and it starts going all over the place, and you're not sure exactly why horizontal autoscaler is going a bit nuts. So anything that makes your life a little bit easier, of course, is going to have added complications to it. There's also one other autoscaler we didn't have a slide here for, which is called the vertical autoscaler. So horizontal, of course, is adding more pods. Vertical is adding more resources to a pod, more CPU and more memory automatically if a pod is starved of those resources. And so I'm going to go off through this.
Yeah, so we are done with the slide. We want to introduce the company. We're doing projects for US and European companies, retail, digital marketing, technology sector. And we have professionals in cloud engineering, machine learning, and data engineering, creating infrastructure and making applications for our customers. Some full technologies we work with and commit to, so we encourage.
And here's my advertising. I've got to go shutting it off. Yeah, turn it back on there. I thought I didn't turn it on. So I've got a book coming out right now. It's actually being renamed. So I can't put the title of the book up. But you can follow me on Chris Love CNN on Twitter, GitHub, LinkedIn, wherever. And I'll be releasing the book out with another Kubernetes committer. 𝐤𝐳𝐵 is a great guy. We're trying to write a book, or not trying to write, we are writing a book that's more a Kubernetes 200 level version. So it's not Kubernetes 101. You need to know what a deployment is, but you'll learn everything you never wanted to know about Kubernetes networking. You'll really understand what you really didn't want to know about Kubernetes DNS, but you need to know when you wake up at 2 o'clock in the morning and try to deploy a server. One quick note, we talked about some of the benefits of Kubernetes, but we didn't go into it heavily. I wanted to mention that, we talked about scaling, we talked about kind of on the side, talked about high availability, upgrades. There's certain systems out there that are just a nightmare to upgrade. When you're talking about Kubernetes, you have to understand how to upgrade it, but it was built to be upgraded. And there's different patterns you can use to upgrade Kubernetes skills. The value, so Kubernetes is not trivial to run. It gives you amazing simplicity in certain aspects, but you gotta know a little bit about what you're doing to run it. Using a managed service helps a lot. But the power of high availability, the power of automatic upgrading elastic load balancers, power of a node that gets unhappy, and your pods roll across other node, it's just invaluable. Anything else to close it?
Yeah, I would like to add that to run from our experience, run perfect Kubernetes installation, all the rest of the ecosystem has to be run simply. You have to consider proper logging, proper central logging, proper monitoring, proper CI/CD pipelines, and everything should be software defined. Because you can't just replace one part of your legacy application or some outdated process that where you do things manually with Kubernetes and remain with everything else. It's not suitable process. So Kubernetes often at organizations where we introduce microservices is an enabler to go across the company and replace processes that are lacking with implemented processes.
Any questions, real quick? We're right on time, but anybody have any specific questions?
Can you scale on memory?
Yes. On which aspect? Pod, node?
Vertical. Horizontal scaling.
Horizontally. So scaling on memory, so you get more memory in the cluster when you scale the cluster horizontally, and you're able to have more pods that way. Typically scaling with memory is vertical. Pod auto scaling though, you can go from like 2 gigs to 8 gigs in a pod. So not really. So you can horizontally scale, but one thing you look at doing is having different node pools or groups of nodes for different workloads. And you can target workloads that need more memory and more CPU to those. And more of those bigger nodes can be created with the workload that's running within those nodes. So it's almost like you can have smaller nodes and you can have bigger nodes, and you put all your big stuff on the big nodes. And if the big stuff goes and it's working real hard, you'll scale that out. Great question. Yes? horrible, unfortunately horrible time period. So, we're continuing to debugging. So you can actually exec into a container and start up the process by hand. So you can do control exec and get right into the container. But really, debugging remote processes is all about logging. So it doesn't matter if you're running a remote process via RMI or a remote process on another server or serverless. You gotta standard out print statements are really helpful at times.
So development clusters, we do sometimes for Java applications expose 𝐤𝐸X port to be able to connect from 𝐤 console and also connect the volume to a code where you can dump your Java view and then analyze it on your laptop.
Yes.
There's a lot of people out there where you try to run this on the edge, and obviously the future of Kubernetes
So Kubernetes on edge, like using on the edge. So with micro devices, or we're talking about the future of Kubernetes in general.
Yes, so it is getting more popular. I know that Verizon are working on a fog computing where they install Kubernetes cluster on each and every cell and several towers. So they have servers that are serving that traffic for 5 or 4G networks, right? So they reuse those servers to run Kubernetes where they run machine learning model inference. And they pre-process data before they are uploaded to the cloud.
So I'll take, you kind of asked about the future of Kubernetes as well. So a lot of very, very large companies are putting a lot of money into Kubernetes. When VMware announces that the next substantial improvement to ESX is that you now can install Kubernetes automatically, or Kubernetes is now installed automatically with it. They're moving vSphere, which is usually a virtual machine itself, and now runs in a pod on the ESX server. It was a very large code change. I've never seen a component in a specific industry dominate the industry like Kubernetes is, except for Oracle database. Everybody had an Oracle database back in the day. And if you're running in-house cloud, pretty much everybody runs vSphere. So it's kind of in those terms. People are talking about 30 years it'll be in production. Just kind of crazy how fast we go. Any other questions, or we'll take them up here? Thank you so much, I really appreciate it.